we are going to talk about graphing functions that take a complex variable and output a complex variable. But first, let me just talk about what happens if the input's a real number and the output's a real number. Well, here are all the possible inputs. This is how we normally think of it. And what we normally do is we normally think of, well, let's just look at some sort of subsection of the real numbers, and then we'll graph it. And then we graph it along kind of an output axis. We normally call it the y-axis. And then what happens is that we can graph some sort of a shape over the area that we're interested in. This works really well because you have a one-dimensional input and a one-dimensional output for a total of 2 dimensions, which fits really well on the page. The problem when we come over here, the complex numbers are really a 2-dimensional object. So in order to do something similar over here where you have kind of an input plane and an output plane, you need 4 dimensions. I'm not very good at drawing in 4 dimensions, so here's kind of the workaround. Let me give you a couple examples of how you could think about these things graphically. So one, suppose that f of z is equal to z plus 1. What that does is I'm going to look in the complex plane here, and I'm going to look at just a particular subsection of the complex plane that I'm interested in. And maybe the subsection I'm interested in looks something like this. Right? To kind of get an idea of what happens, if you just look at the subsection, just like if I just look at the subsection here, I don't need to look and see what happens kind of all over the place. You might only care about one part. If you only care about this part, what you can do is you can draw another set of complex axes and figure out what happens to your smiley face. If this is the case, maybe I should anchor this a little bit. Maybe this is kind of centered at 2. If this is the case, you're going to have your smiley face. Every point's going to have 1 added to it. So 0 is going to be mapped to 1. 2 is going to be mapped to 3. Every point is going to be moved to the right 1. So you're not going to have another smiley face, an image smiley face. That's not distorted because this is just a simple translation that is just shifted over to the right 1. Very similarly, we can do if, I don't know, I'm running out of letters. How about h of z equals z minus I? What would that do to my smiley face? Well, my smiley face would start like right there, and the end result, that was redundant. The result, when you map, is you're still going to be centered at 2, you're just going to be brought down a little bit. So the output is going to be, everything's just going to be shifted down 1, because right, the I kind of corresponds to the y-axis. So you're going to drop the y values down by 1. Okay, let's just give you one last example here. How about k of z equals z squared? And now I'm going to start not with a smiley face. I'm interested in a quarter circle. This is supposed to be a circle, and it goes from 3 up to 3i. I'm just going to look at that. And then when I map it over by the function k, I have an output plane. I can see what it does. Well, recall in polar form, if you have e to the I theta squared, you're going to get r squared e to the I times 2 theta. That's barely legible. So what happens is the radius gets squared. Well, let's color code this again. The radius gets squared, so instead of going from 3 and 3i, I'm going to go from 9 to 9i. This is not to scale. And my angle is doubled. So instead of going from 0 to pi over 2, I'm going to go from 0 to 2 times pi over 2, since that's what it does. So I'm going to go to 0 to pi. So that's what the image looks like. So this is just some way of figuring out what a function does. And it differs from the reals. The reals, you can basically graph the entire thing. Here we really can only look at one sort of part of the plane at a time and figure out what happens. Thank you. Bye-bye.